So this question we actually need to use the graphic method. So this hint says if section 6.2, but what section 6.2 is about is it's about trying to figure out a quantity by looking at the graph of it. But let me just do a quick go through of this method. What it means is that in this case, for example, for A, we need to use a graphic method to estimate the total impulse. What is total impulse? Total impulse is the change of momentum. And that is mass times delta V, but it's also F times delta T. So it's the multiplication of F and delta T. Now we have this graph with the x-axis as T and the y-axis as F. If there is an area here, how do we calculate, if it's a square? The area of the square is also F times T. So what this means is that by counting the area in this FT graph, the area will give us the momentum because both of them are a multiplication of F and delta T. So that's what we're trying to do here. So A, we need to find the total impulse, and what we're doing is we're just trying to count, we just need to know the area under this curve. And this precise calculation of this area needs calculus, but we're not doing that. We're just doing a simple estimation. So we're doing count squares. So so there are different ways of doing it. One way to do it is to try to estimate this curve is a triangle. So we try to estimate a triangle. Probably here because if we estimate here, we might overestimate it too much. So we roughly try to make sure there is the same amount of area that is above our line and below our line. So they roughly cancel each other. And then we look at this area under the triangle. So this is one way of estimating it. I personally think it's more accurate. Of course, the other way to estimate it is just to count the number of squares, and then you can say there are this many full squares, and then there are this many half squares. And half squares, some of them might have like more than half, some of them might have less than half, but you always say it's half square because you assume that if you take the average, they're going to cancel out, and then you use like the number of squares and the area of the square to calculate it. But here I'm using the triangle method. So if I use the triangle method, this is 0.05, so roughly each square is 0.01. So I am drawing this line roughly at the middle of it. And same, this is roughly at the middle of it. So between the widths, it's a total of 4 grids over here. So it's 0.04 second. And the height is 250 Newton. Sorry. So if I want to calculate the area of this triangle, I do height times base over 2. So I have delta P equals 1/2 of 250 Newton times 0.04 seconds, and that gives me 5 newtons times second. So that is an estimation of the change of momentum, or like the total impulse given to the ball. So the second one asks us to find the velocity of the ball after being struck, and that is we just use delta P equals delta V. And here, because there's no initial speed, so first speed is just going to be delta V. It's going to be the same. So we have Vf equals delta V equals delta P over N. Delta P we know is 5 newtons times second, and the mass is 0.06 kilogram. So this is equal 80 minutes per second. So yeah, so that is the velocity of the ball after it is struck.